Hi class, welcome back to Calc 3. I'm Dr. Scott Adamson, and this video is part 2 of a series of videos focused on directional derivatives and gradient vectors, including some partial derivatives, just sorting out what all of these ideas mean. And we're using this context of a boat on a lake traveling through the water, and we're thinking about the depth of the water as the boat travels. So we had a depth function at a location on the surface of the water. The depth of the water was 6x squared plus 5 times the cosine of y. The boat was currently at this location, and last video the boat was traveling in this particular direction. Now in this video we're going to change the questioning just a little bit. Please remember to click the link below the video to access the notes for this, and you can see this question being asked. The question is, what direction should the boat travel to achieve the greatest change in the depth of the water? So we saw in the last video that when the direction is given, we can determine the rate of change of the depth of the water. But this question is a little bit flipped around. I want to make sure you're sorting this out in your brain. In this question, it's in what direction shall the boat travel to achieve the greatest rate of change? And what is that rate of change? So before we start with the computations, we're going to again go look at the graph of this thing and see if we can at least get some sense about the direction that would achieve this greatest rate of change. So we're examining the idea of the boat traveling from the point 0.25 in a direction such that the rate of increase in the depth of the water will be the greatest it could possibly be. So here's that image again. The boat is located here at point A, which is 0.25. There's the boat. Now remember, this blue surface here represents the depth of the water. So if the boat is here and say it travels in this direction, can you see how in this direction the depth is actually going down? The waters are getting more shallow. And also keep in mind that if you look at the Google Earth image, we're restricted to just the first quadrant, positive x, positive y quadrant. So we can't really go beyond that because we'll be on the shore, no longer in the water. And so in this, if you kind of look at this gray space down here is our only feasible directions that we could travel, we would have to travel in a direction approximately what you see here. I kind of just eyeballed it, guessing that the greatest rate of change might be somewhat in this direction. And again, this is no computation. This is no for sure. I'm just trying to think, trying to see it, move this thing around to see how could I get the greatest possible increase in the depth and still be in my feasible region. Now, to help you see it in a more traditional view, let's go to the traditional XY plane. Notice X is positive, Y is positive. So in that plane, my just kind of playing around, eyeballing it, looks like for the boat to travel in a direction for the greatest increase in depth to occur, I would have to increase X but decrease Y. So let's see if we can compute that now and verify that that would indeed give me the greatest rate of change. Now, in GeoGebra, just so you know, you can grab that point B and you can move it. If you thought it was, well, it's more like in that direction. And we can then look and see. I kind of got off the surface a little bit there, but just to make my point, again, in that XY plane, it looks like I'm going to need to increase X and decrease Y in some fashion in order to experience the greatest increase in water depth. Well, let's go back to the board and compute and see if we're right. So just kind of getting a ballpark feel for what direction the boat should travel to achieve the greatest rate of change. It appears as though the boat should travel such that here we are, or here the boat is at 0.25, And we saw from that surface that if the boat increased in the x direction, but decreased in the y direction, that would achieve the greatest increase in the depth. But that's a ballpark. We want to really figure this out. Well, now here's where the gradient vector comes in. The gradient vector, as you saw in the previous video, is used in the directional derivative, but the gradient vector itself has some important properties. In fact, the gradient vector is, first of all, a vector. And the gradient vector has direction and magnitude. The direction that the gradient vector reveals is the direction of the greatest increase. That's it. So, looking back at the last video, the gradient vector turned out to be 3i minus 1.237j. That is the direction of the greatest increase, and we kind of get a sense of that. Notice in the x direction, we would have to increase by 3. In the y direction, we'd have to decrease by 1.237 approximately. And so that's exactly what we were seeing when we were examining that graph previously. So, first part of this question. If the boat is at this spot and the boat is going to travel such that the water depth will increase at the greatest rate, that's the direction the boat should travel, the direction of the gradient vector. Now, what is the rate of change? What is this greatest rate of change? That's the magnitude of that vector. The beautiful thing about this is it's the magnitude of that vector. So, to get the greatest rate of change, we're going to compute the magnitude of that gradient vector. So we'll take the square root of 3 squared plus the negative 1.237 squared. That will be the greatest rate of change. Now, if you watched the last video, if you didn't, you should go watch it. We saw that if the boat is at 0.25 and travels in the direction of 2i plus 2j, if it goes that way, the water depth increased, but like by 1.25-ish feet of water per mile traveled. Now this is going to be the greatest rate of change in the depth of the water at that location. So we should certainly see a result greater than 1.25. Let's see. So hope you have a calculator nearby, but if you work this out, the square root of 3 squared plus negative 1.237 squared, we get about 3.245. Which is indeed greater than the 1.25 we saw previously. Now, no matter what direction this boat were to travel, it's never going to achieve a change in water depth greater than 3.245. This is the greatest rate of change of water depth. Now, we can't just leave this number naked like this. We need to put some units on it. So let's get our units going. So the depth of the water was measured in feet. So the water depth, feet of depth, we'll say. So the water's getting 3.245 feet deeper per 1 mile traveled. But then again, this is where we have to get into direction. This is not just any old direction. This is specifically in the direction of the gradient vector. So if we travel in the direction of that gradient vector, then we'll achieve that rate of change of 3.245 feet of depth per mile traveled. So the second part of this problem we're going to examine is, in what direction should the boat travel so that the depth of the water remains constant? Now, before we explore it computationally, let's explore that question graphically just to get a sense for what's going on. We're going to examine the idea of the boat traveling in some direction that we will determine such that the depth of the water remains unchanged. So in this case, we're looking at a contour plot. So I've entered into Desmos the function 6x squared plus 5 cosine y equals 4.5. And so that produced this graph. This is all the ordered pairs x comma y such that the depth of the water remains 4.5. This one is about 5. This one is about 5.5. So we are looking for, here's the boat at 0.25 as we've seen. we're looking for a direction such that the boat remains on that level curve, thus the depth of the water not changing. Notice if the boat moves off that level curve, the water is either going to get more deep or more shallow. Now what I've demonstrated here is, first of all, this one. This is the gradient vector. Now, the purpose of this video and the previous video is to just make sense of all these different things: directional derivatives, partial derivatives, gradient vectors. What are they? Well, one of the properties of the gradient vector is it gives you the direction of the greatest rate of change. Notice, to get from this level curve to this level curve in the shortest amount of space, thus the greatest rate of change, the boat would have to travel in a direction perpendicular to the current level curve. So this is a representation of the gradient vector, perpendicular to the level curve. You might imagine that if the boat traveled, say, this way, in order to get to that next level in this graph, it would have to travel a much greater distance, thus not maximizing the rate of change. The greatest rate of change would be perpendicular, getting to that next level curve in the shortest amount of space, the shortest amount of distance, thus the greatest rate of change. So now we want the direction so that the level does not change. So we need to move in a direction perpendicular to the gradient vector. Now notice when we do that, the boat could travel in two directions. It could travel this way and stay on the level curve perpendicular to that gradient vector, or it could travel exactly the opposite direction and still be perpendicular to that gradient vector. Now we're going to go back to the board and compute those directions precisely, but just conceptually the idea is this. You know the gradient vector. You just need to find a vector perpendicular to it, thus keeping us on the level curve in one direction or the opposite, and thus being perpendicular to the gradient vector. So keep that in mind as we move forward and start computing. So I tried to convince you graphically that at the point 0.25, the boat is going to have to travel in a direction perpendicular to the gradient vector. So the gradient vector gives you that direction of greatest increase, and that gradient vector is perpendicular to the level curve. Well, if we stay on the level curve, then the depth won't be changing. So we need a direction that's perpendicular to the level curve, perpendicular to the gradient vector, I'm sorry. So how do we create vectors that are perpendicular to each other? So the gradient vector we've got right here, it's approximately 3i minus 1.237j. We need to create a vector perpendicular to that. So here's the reminder. Two vectors are perpendicular when their dot product is 0. So we need a gradient vector dotted with some other vector, I'll call it vector b, so that their dot product is 0. That will guarantee us that the vectors are perpendicular. That will guarantee us that the boat is traveling on, maintaining a level, and therefore the depth not changing. So all we have to do is find a vector b. All right, here's how this works. So the gradient vector, here it is. The gradient vector is 3i minus 1.237j. I need to dot that with another vector so that the dot product is 0. Keep in mind, dot product is this nice little thing where we say this product plus this product. What I'm referring to is there's some I component and some j component over here. So this product and this product add up to make 0. So here's the slickest way to make this happen and get the direction that we need. So if I just flip those numbers around, make this 1.237 and make this 3. Now I have 3 times 1.237. I have 1.237 times 3. I have the same quantity, I have the same product. So if we're adding two quantities that are the same, if one of them is just the negative of the other, they will combine and make 0. So right now, 3 times 1.237 is a positive number, minus 1.237 times a positive 3 will be a negative number, and so those two will cancel out and make 0. So vector B could be the vector 1.237i plus 3j. So notice what I've done here, and think about why this makes sense. I've taken the gradient vector and flipped the components, and then made one of the components the opposite sign. I made the minus 1.237 positive. And then that dot product will indeed produce 0. Beautiful. But as you saw in the video, to be on that level curve, to be perpendicular to that gradient vector, we could go in one direction, or we could go in exactly the opposite direction and still be on that level curve, still be perpendicular to the gradient vector. So another option would be move opposite that vector B. So that is opposite. Make it a negative 1.237i. Make it a minus 3j. That also would move you in a direction perpendicular to the gradient vector, and we can check that. Here's how we can check it. If we dot that gradient vector, where is it? That gradient vector with the negative of b. Let's see if this dot product is indeed 0. So the dot product between this one and this one. 3 times negative 1.237. Let me just write it down. 3 times negative 1.237 minus 1.237 times minus 3. Notice, same product, it's 3 times 1.237. This one's negative, this one's positive. So of course, that dot product is 0. It's just confirming what we're saying, that this vector is also perpendicular to the gradient vector. So now, put it all together. In the last 2 videos, whatever the context is, the thinking is the same. If you want to compute the rate of change given a direction, like we did in part 1, directional derivative. If you want to compute the greatest rate of change, what direction would that be? Gradient vector. The magnitude of that vector is that greatest rate of change. And then, if you want the rate of change to be 0, that is, you want the depth, or whatever your context is, you want your function not to change. Just find a vector such that it's perpendicular to that gradient vector, the dot product is 0. And here's a quick, slick way to make that happen. So spend some time sorting all this out in your head. Use the notes, use the video, and sort out these ideas. Directional derivative, gradient vector, greatest rate of change. What does it all mean? Get it clear in your head and you will be good to go.